Hey everybody, welcome back for another chemistry lesson. Today's lesson is on solutions and precipitation reactions. So first and foremost, let's talk about solutions. So whenever we're talking about solutions, we need to understand what a solution is. It is a homogeneous mixture that is liquidy. And I'm using the word liquidy lightly because liquid would indicate that it is, one substance, and it's not. That's the whole point. It is a mixture. So, for example, whenever I take table salt, put it in water, the table salt seems to disappear. It doesn't. It just mixes in very thoroughly so that it looks all the same. So it's homogeneous. So these homogeneous mixtures we call solutions. The majority component, so in the salt water example, the water is what we call the solvent. The minority component, so the thing we have just a little bit of, is the solute, the thing that is being dissolved. And then if the solvent is water, then we call the solution an aqueous solution. And you have probably seen at this point chemical equations for reactions and then the little parentheses down at the bottom, AQ. That means it is an aqueous solution, so it's dissolved in water. Now, because solutions are mixtures, it is possible that the composition varies from one sample to another. That's not a weird thing. Pure substances have constant composition, but seawater, for example, is not necessarily going to have the same composition from, let's say, the Outer Banks to the Gulf of Mexico to the Pacific Ocean, right? So, because of this, what we have to talk about so that we can accurately discuss solutions is the concentration of the solution, which is how we quantify the amount of solute relative to the solvent. So we can speak generally or qualitatively about solutions by calling them dilute solutions or concentrated solutions, where dilute solutions have just a little bit of the solute and concentrated solutions have a lot of it. So if I was comparing fresh water versus salt water, there's still salt in the fresh water. It's just very, very little of it. So that would be considered dilute compared to the more concentrated saltwater solution. We can also talk about solutions quantitatively through what we call molarity. Molarity is the number of moles of solute divided by the number of liters of solvent, right? So here in this example, we have 2 moles of sodium chloride in the bottom of this volumetric flask. So what we do is then bring the volume of the solution up to 1 liter. This is not the same as adding 1 liter to there. And this is for reasons beyond what we talk about in this class. Volumes are not additive. So we have to be very careful in how we do this. But what we end up with is a solution that is 1 liter that contains 2 moles of sodium chloride. So we quite literally say 2 moles of sodium chloride divided by 1 liter of solution gives me 2 molar sodium chloride. So let's talk about the exact methodology for making a solution. Okay, so exactly how we make 1 liter of solution is like this. So you're going to put the correct mass of solute into a volumetric flask. You got to figure out, if I want 1 molar, you need to figure out the mass, right? In this case, 1 mole of sodium chloride, the mass of that is 58.44 grams. So I'm going to put 58.44 grams of whatever it is I'm dissolving, in this case sodium chloride, into the bottom of the volumetric flask. Then we will add enough distilled water to dissolve the solid. Number 1 needs to be distilled water so that there's nothing else in it. And number 2, we're not going to fill it up completely. It's really hard to effectively stir when you have a full flask of water, right? So we're going to add enough distilled water, maybe halfway or something like that, so that we can then mix and dissolve thoroughly. then we will bring the volume up to the 1 liter mark. Now, the total volume is not going to be less than or greater than. There is a line here that makes it exactly 1 liter. That's why you have to use a volumetric flask when you're doing this. So again, not adding 1 liter. We are going to bring it up to 1 liter volume. Once we have a solution, then we can use it to make other solutions. So if you purchase chemicals as a solution rather than as the solid, they are often stored as concentrated stock solutions, right? So if I have sulfuric acid, the stock solution is typically 18 molar, right? Well, we hardly ever need 18 molar acid, right? So what we do is we do a dilution of that stock solution. So to make solutions of lower concentration, what we do is just add more solvent, but we do it in a very specific way. So the amount of solute doesn't change, just the volume of the solution. So when we're doing this math, the moles of, so let's say, sodium chloride before and the moles after are going to be the same. We're just adding water to the after piece, right? So the concentrations and volumes of the stock and new solutions are inversely proportional. So this is the formula that we use. We take the molarity of one solution and the volume that we used of it, and then we can calculate the molarity of the second solution using the volume of it. Or if I know what molarity I need, I can figure out what volume I need to make it. So let's look at this example here. All right, I've got calcium chloride in a 10 molar stock solution, and I need to make 3 liters of half molar, right? So this is significantly more dilute. So I just plug it into my formula to figure it out, right? I have 10 molar. I don't know how much in that I'm going to use, but I know that at the end I need 3 liters of 0.5 molar. So I solve for my question mark here. All right, my molarity cancels out and I end up with liters. And what I end up with is 0.150 liters or 150 milliliters. So what that tells us is I'm going to take 150 milliliters of that stock solution, put it in my volumetric flask, and then bring it up so that the final volume is 3 liters. So I'm still going to have however many moles were in that 150 milliliters, but now instead of it being X number of moles in 150 milliliters, it's X number of moles in 3 liters. Okay, so now that we've talked about making solutions, let's talk about what happens when we make solutions. So there are 2 types of aqueous solutions, and you should be familiar with them generally speaking. Salt water, sugar water, right? They're both homogeneous mixtures with water, and they both, disappear in the water and dissolve. But what happens on the molecular level when a substance dissolves? This is really important. And those 2 types of solutions I mentioned, the answer to this question is actually different for the 2 solutions. So when a solute dissolves, right, there are attractive forces between the solute particles holding them together. So when I drop salt into water, there are attractive forces holding my NAs and my Cls towards each other. There are also attractive forces between the water molecules. So when we mix the solute with the solvent, we end up with attractive forces between solute and solvent, in addition to the forces that already existed. If the attractions between the solute and the solvent are strong enough, our solute will dissolve, right? So if salt plus water is stronger than salt plus salt, then it will dissolve. And this is what happens here. Water is actually a polar molecule, and what that means is we have an uneven distribution of electrons, leading to partial charges, right? So in a water molecule, let me change the color because there's red there. Oh no. Oh, guess I can't do that. Never mind. This is my oxygen, and it's an electron hog. It holds on to the electrons more of the time than the hydrogens do. And this is something that gets addressed when we talk about bonding in Lewis structures. These are my hydrogens, and they hold on to the electrons less of the time. Remember, our electrons are negative. So wherever they hang out more, gets a negative charge. Wherever they hang out less, gets a positive charge. Not a whole positive, but a partial positive. So that's what this represents. This is a partial positive charge and a partial negative. And so whenever sodium chloride is put into water, the partial negative on that water will be attracted to the positive charge on sodium. The partial positive on my hydrogens will be attracted to the negative charge on my chloride ions. So this is solvent-solute interaction, right? Because remember, these guys were already attracted to each other. These guys were already attracted to each other. But now we're adding an additional interaction into the mix. So each ion is attracted to the surrounding water molecules and pulled off of that crystal as it's dissolving. So when it enters into solution, we end up with a positive sodium ion that's surrounded by water molecules, a negative chloride ion that is surrounded by water molecules. So we have free moving charges at this point that are able to conduct electricity, right? Electricity is nothing but movement of charge. And because we now have, instead of a chunk of positives and negatives, we now have freestanding charged particles, now those things can move, which is that flow of electricity. So this is where we get the idea of electrolyte versus non-electrolyte solutions. Materials that dissolve in water that make that kind of solution where we can conduct electricity, we call those electrolytes. So that would be like salt. Materials that dissolve in water to form a solution with no ions don't have charges that can flow. If we don't have ions, then we don't have charges, then we cannot conduct electricity. Those solutions, like sugar solutions, are non-electrolytes. So ionic substances like sodium chloride that completely dissolve in water are strong electrolytes. Strong acids are also strong electrolytes. And then, except for acids, most molecular compounds, like sugar, actually don't break up into charged pieces, but rather dissolve as intact molecules. And because of that, intact molecule means no charge, means no flow of electricity, non-electrolyte. All right, so again, ionic compounds that will dissolve will conduct electricity, so they are electrolytes. Acids, which I will link the video that I made on acids up here if you want to go and watch that one. Acids ionize to varying degrees. It depends on what the acid is. If they are strong acids, they will completely dissociate, and so they will be strong electrolytes. Some acids, actually most acids, do not completely ionize. So they make a little bit of charged particles, but not a ton. We call those weak acids, and they are weak electrolytes. So this is what it looks like when sugar dissolves in water. There are some interactions that happen between water and the sugar molecules, but the sugar molecule itself does not break apart, which is why we don't end up with charged particles that will then not conduct electricity. All right, so I've mentioned these terms before already, but strong electrolytes are materials that completely dissolve as ions. This is some ionic compounds and strong acids. These solutions are good conductors of electricity. Weak electrolytes are materials that dissolve mostly as molecules but sometimes give off ions. These are weak acids. These solutions will conduct electricity, but not very well. Okay, I actually have pictures of the thing I talked about a minute ago on the next slide, so hold that thought. When ionic compounds dissolve, we call that dissociation, when they're separating and dissociating from each other. So when sodium and sulfur break apart, we end up with sodium and sulfide. There we go. That is dissociation. When our compounds that have polyatomic ions dissociate, the polyatomic ion stays together. So sodium sulfate ends up being sodium and sulfates, right? It's SO4, not S's and O's, right? And then when strong acids dissolve, the water molecule, not the water molecule. When they dissolve in water, the molecule will ionize into hydrogens and whatever's left over. So in this case, sulfuric acid, we get hydrogen ions and sulfates. So, moral of the story here is non-electrolytes are our molecular compounds and things that are not soluble. So we get non-charged particles that don't have ions, therefore no moving charges, no flow of electricity through the solution. And we can see that here. We've got this circuit set up, but no light in the light bulb. Here, weak electrolytes like weak acids, some of them break apart into their ions, therefore we get a little bit of a flow of electricity. So very dim light here. And then finally, our strong electrolytes, like our strong acids and our soluble ionic compounds, are strong electrolytes, lots of electricity flow, and so bright light on the light bulb. Now, I mentioned ionic compounds that are soluble and not soluble. Let's talk about it. So, when an ionic compound dissolves in water, our resulting solution ends up with ionic compounds that are not stuck together, but rather the ions that are, pieces. But not all ionic compounds will do that. So for example, silver chloride, not soluble. So that word that I'm using, soluble, if it will dissolve in water, soluble. If it will not dissolve in water, insoluble. Know those terms. So, examples of this. If we mix silver nitrate with water, that is a soluble salt. So, it will dissolve, and it is a strong electrolyte. So, we have good flow of electricity. Silver chloride is almost completely insoluble, and basically none of it dissolves, and we end up with this blob of silver chloride on the bottom of our container. When we are figuring out if a salt dissolves or not, we, as in current day, we have a lot of information at our fingertips. But all of this information comes from basically experiments that other people have done, right? There are lots of factors that determine whether something will dissolve or not. So instead of us needing to figure that out, we just have a list of rules. Right, so here we can see the list of rules. The top part of this table tells us things that are generally soluble and if they have any exceptions. So anything that is lithium, sodium, potassium, or ammonium ions, anything with those in it will dissolve. There are no exceptions. All right? Anything with sulfate in it is going to dissolve except when we've got strontium, barium, lead, silver, or calcium ions. So that's how we read this table. The bottom half, generally insoluble, and there are some exceptions listed here. Now, when do we use our solubility information? Because that's a whole lot of information, but why do I care, right? When we have precipitation reactions. Precipitation reactions are reactions where we have two aqueous solutions, we mix them together, and we create something that is not soluble, right? So in this example here, we have a clear solution being added to a clear solution, and very clearly you can see here we're getting this yellow cloud where they are mixing, right? So when we have two aqueous solutions, we have just the ions that those compounds produce, right? So in this particular situation, I have potassium iodide, so potassium ions and iodide ions. And then I have lead nitrate, so lead ions and nitrate ions. When those things come together, what we end up with is potassium nitrate, which is soluble according to our rules, and lead iodide, which is not soluble. That piece is what's coming out in this yellow cloud here. We call that the precipitate or the precipitate. And if I'm mixing two things together and getting a precipitate, it is important that I know the solubility rules, because then I can figure out what's in here. All right, well, that didn't work. What did I get? So I can figure it out. If I mix two solutions and do not get a precipitate, no precipitation means that no reaction happened. So when you're writing your molecular equation and your net ionic, or your complete ionic, your net ionic equations, if I don't have a precipitate, I don't have a reaction that occurs. Precipitation reactions do not always occur when I'm mixing two solutions. When nothing happens, the answer is no reaction. So potential precipitation reactions are usually double replacement reactions. So our products are pretty easy to predict. We just and do a little switcheroo on the cations or the anions. And so what we do is, if we have our two solutions, we know what's in there, we can predict what products they will make. And then we can determine which thing is going to precipitate out, or if there is even going to be a reaction based on those solubility rules. I will link up here. I'll link the video on where I go through how to figure this out. So there will be a video for that that'll help you out, and I'm also going to go over it in class.